Hi everyone, Dr. Burns here with our next lesson in our chemical kinetics chapter, where we're going to be discussing rate laws and integrated rate laws. So we've just learned about rate. What is a rate? How does rate change with the changing concentrations of our chemical reactions? But now we want to discuss the factors that will affect the rate. And one of the three factors that we are going to discuss is first, physical state. Reactions will occur when there is contact between the reactants. When the reactants are in different states, the reaction can only take place at the interface of those two phases. So if we have gases reacting with gases, then that's no problem. But if we have something like in the image I have here, where we have a liquid reacting with a solid, the reaction is only going to take place where the solid and the liquid meet. And how that solid is presented is going to affect the rate itself. So I have a reaction here where I have iron in two different forms. First, I have granules. Okay, so if we were to look at this before we put liquid in there, it's just like a little bunch of granules of iron ground up. Okay. And then in the second image, I have a rod or a nail that is made out of iron. So we can see from these two images that the iron granules are reacting more vigorously than the iron nail. Okay, we see that by first the darker complexion of the solution around us, showing that there's a reaction going on, and the fact that there's more bubbles that are present in that reaction vessel, whereas in the nail we don't see that as much. And this is because the granules allow for that liquid to get into all of the crevices that are between it. So if I were to draw the solution, it would get in all the way around those granules and react with all of the granules equally at the same time, allowing the reaction to happen faster. Whereas if I have a nail or a rod, okay, so if I have a nail, it looks like this, and it's made up of a bunch of iron, right, going through. There's layers upon layers of iron atoms. And if we were to put that into the solution would only have contact with that first outer layer of iron first. And it's a lot smaller of a surface area to react with, so it's going to react less vigorously, and also the rate of that reaction is going to be much slower. So the granules have a faster rate of reaction, and the nail, the rod, has a slower rate of reaction. Okay. The other factors that will affect our rate are going to be the concentration of our reactants and the temperature of our reactants. And a key word here for both of these is going to be reactants. What we're going to see in this lesson and our following lessons is that we really only care about the reactants moving forward. We're only looking at unidirectional reactions, so they're only going from reactants to products. So what we're going to be looking at specifically in how the rate is going to be affected is of the reactants themselves, because that's what's initiating the reaction. So the concentration of the reactants will affect the rate, because rates will usually increase when the concentration of one or more, there's a typo there, that should say more, of the reactants increases, right? If there's more individual molecules, meaning we have more of a concentration of that reactant or reactants, then there's going to be greater chances that those collisions are going to happen more effectively, causing products to form and at a faster rate. So a higher concentration will always equal a higher number of moles or molecules of reactant in order to promote the production of product. Another factor is the temperature of the reactants. We know that temperature is going to cause our molecules to move faster or slower depending on if the temperature is higher or lower. So rates will usually increase at higher temperatures because the molecules are moving faster. Higher temperatures will equal higher energy and greater number of effective collisions between reactants. So both of these factors need to be taken into account when we consider rate. In this lesson, we are going to focus strictly on concentration of reactants, and in our next lesson, that's when we will be discussing the effect of temperature on the rate of the reaction. So let's continue our discussion on the concentration of the reactants. We have to introduce something called a rate law. And a rate law is an equation that relates the rate of the reaction to the concentration of the reactants. Now, in our previous lesson, I said that we had to make sure we know the difference between a rate expression compared to another term we were going to be using in the future, and rate law is that term. So a rate law and a rate expression are different. We need to be able to keep those terms separate because they have separate meanings and separate applications given the reaction. So let's look at what a rate law is. So again, we have that reaction that we've looked at previously. A plus B goes to C plus D. And our rate law is expressed as the rate is equal to K times the concentration raised to the X multiplied by the concentration raised to the Y. And specifically, the concentrations are of reactants only. Now, another thing to note here is that as we've seen both in this chapter and in previous chapters, whenever we have an expression, a mathematical expression based off of a balanced equation, we have to utilize our coefficients. But rate laws do not use coefficients to tell us anything about the reaction rate. Shouldn't say inform, I should say determine. Let's say determine, that's a better word. Determine the rate. So essentially this comes down to ignore balancing. We're not going to use it. When we're looking at rate laws, we're ignoring all of our stoichiometric coefficients. When we're looking at rate expressions, we do have to take those stoichiometric coefficients into account, and that's why they are different, and we need to remember the difference. Rate laws do not take balancing into account. Rate expressions do. Okay, so just make sure we're clear on that as you're going through and practicing these types of problems. So the reaction rate is equal to K times the concentration of A raised to the X times the concentration of B raised to the Y. Now, if we only had one reactant, then it would only be A. If we had three reactants, then we would add a third variable. Okay, this is again just a generic equation. But let's define our variables. Here, K is the rate constant. And the rate constant is just that. It is a constant for a given reaction, and it'll be specific to reactions at certain temperatures. When we have the variables x and y, those are our superscripts or our exponents, these are what are referred to as the reaction orders. Okay, the reaction orders with respect to either reactant A or B. So X would be the reaction order with respect to reactant A, and Y would be the reaction order with respect to reactant B. The reaction order is how we're going to have a relationship between the rate of the chemical reaction and the concentration of that particular species. And we'll look into reaction orders more in depth here in a few seconds. Now, if we take those reaction orders, X and Y, and we add them together, that will represent the overall reaction order for the entire reaction. So let's look more into reaction orders. Reaction orders are typically positive integers, so we're talking 1, 2, 3, and so on, okay? Though they can be fractions, they can be negative, and they can be 0. Typically the fraction that we see is 1/2, and typically the negative that we see would be a -1. But those are rare in the experimental sense. I know your ALEKS homework does throw in some of those fractions and those negatives, so just keep a lookout for that. Reaction orders will describe the mathematical dependence of the rate on the reaction concentrations. So here we have our rate law. Again, we'll write that just to make sure we're remembering the difference. This is a rate law. Okay, so if in this rate law we had x is equal to 1 and y is equal to 2, we would say that the reaction is first order in A and second order in B. The overall reaction order is the sum of the orders of each reactant. So in this example, the overall reaction order would be 3 because 1 plus 2 is equal to 3. Some more examples of that are shown here. Here we have 3 different rate laws. Again, these are rate laws, not rate expressions. In our first rate law, we see that the rate is equal to K times the concentration of H2O2. And again, if we have it raised to nothing, remember that is a 1. Right? We don't show 1s when we raise them to that power. So we say that this is first order in hydrogen peroxide and first order overall. There's no other reactants present in that rate law, so we know that the only reactant that is contributing to the rate is going to be the hydrogen peroxide. And again, we're only looking at reactants. Our next rate law is rate is equal to K times the concentration of C4H6 raised to the 2. This means that we have a second order in C4H6 and its second order overall, meaning that C4H6 is the only reactant that contributes to the rate of the reaction, and no other reactant is either present or contributes to that rate of the reaction. If we have more than one reactant, like we do in our last rate law here, we get K is equal to H concentration of H plus raised to the 1 and concentration of OH minus raised to the 1. So this reaction is said to be first order in H plus, first order in OH minus, and second order overall. And what I want to make clear about reaction orders and rate laws is, again, we do not take balancing into account. So, our reaction orders have nothing, underline that because it's important, nothing to do with our stoichiometry, our stoichiometric coefficients. So we were able to find these reaction orders without having a balanced chemical equation because with rate laws, the balancing doesn't matter. These reaction orders have absolutely nothing to do with a balanced chemical equation. You do not need a balanced chemical equation in order to find the reaction order. They are not related to each other. It doesn't matter if there was a 6 in front of that C6H6. It does not matter. That would have absolutely no bearing over the reaction order. And this is oftentimes where I see students get tripped up with reaction orders. If they're given a balanced reaction, they think that that balanced reaction tells them something about the reaction order. And it does not. Because reaction orders have nothing to do with any of those stoichiometric coefficients and nothing to do with balancing. We ignore balancing with rate laws. So let's practice. First, we want to write the rate law for a reaction that is second order in fluorine and third order in chlorine dioxide. Well, in order to write a proper rate law, you first write rate is equal to K. We need that K there. And what I didn't say previously is K, which is the rate constant, is specifically lowercase. And as we have seen in our previous lessons, uppercase letters versus lowercase letters matter, like we saw with calories and uppercase C calories. Q is another one that we're going to see needs to be uppercase versus lowercase. Okay, so we need to take that into account. So K here is a lowercase k. So when we write the rate law, rate is going to be equal to K, which is the rate constant. We don't need to know the rate constant for the rate law to be written. All we need to know is the reaction orders. So we then write our concentrations and our reaction orders. So we know that we're going to have fluorine, which fluorine in its elemental state, when it's just fluorine, is F2. Those are things we have to remember from Gen Chem 1. So fluorine is F2. And it is second order. If it's second order in fluorine, then it is raised to the 2. Then we have chlorine dioxide, ClO2, right? Remember, dioxide is 2 oxygens. And that is third order in chlorine dioxide, meaning it is raised to the 3. So the overall reaction order, not that it asks, but it's always good to get the extra practice, would be 2 plus 3. Oops, doing my math early. 2 plus 3, so this is fifth order overall for that reaction. Okay, let's do a few more. On your in your lecture note pack, you have 2 examples here for finding the reaction orders for these 2 rate laws that are written. So here are 2 rate laws. So what I want you to do is use these rate laws to determine the reaction order with respect to each reactant as well as the overall reaction order. So pause your video and solve these 2 problems and then come back so we can discuss the answers. Now remember, our rate law tells us our reaction order. So for our first example, we have that the rate is equal to K times the concentration of nitrogen raised to the 3 and the concentration of ozone raised to the 1. Remember, when we don't have it there, it's a 1. So the reaction order with respect to N2 is 3, or third order. Since this is coming from your ALEKS homework, I do believe they just want you to write the number, so just 3 would be accepted, unless they tell you differently when you go into the actual problem. The reaction order with respect to ozone is then 1, or first order. Therefore, for the overall reaction order, we'll take those two reaction orders and add them together to get an overall reaction order of 4. And let's quickly do our last one. We have rate is equal to K times NO raised to the 2 and oxygen raised to the 1. So we have a second order in NO, a first order in oxygen, and overall 2 plus 1 is 3 for third order overall. So now that we have our rate laws and we can determine the reaction orders for each reactant, now we can use these any values that are given to solve for the rate or the rate constant. So here's our rate law from our previous example. Okay. The question then says the rate of the reaction is 7.0 times 10 to the 4th molar per second when the concentration of NO is 0.60 and the concentration of oxygen is 1.5. Calculate the value of the rate constant. So this then just becomes a plug and chug equation as long as you account for those reaction orders appropriately. So we know our rate, that's going to be 7.0 times 10 to the 4th molar per second. Even in a rate law, rate still has units of molar per second. And that's going to be equal to K, which we're looking for, times the concentration of NO, which was given in the problem as 0.60 molar. And we have to remember to raise that value to the 2 to account for the fact that the reaction is second order in nitrous oxide. And finally, we do the concentration of oxygen, which is 1.5 molar, raised to the 1 because it is first order overall, or first order with respect to oxygen. So now it just becomes a solving for K, just doing some algebra. So let's grab our calculators so we can do this calculation together. So again, I personally like to simplify both sides first, so I'll take that 0.60 and I'll square it, and I'll multiply that by 1.5. So I get 7.0 times 10 to the 4th molar per second is equal to 0.54 times K. And now to solve for K, I'll take that 7.0 times 10 to the 4th, and I'll divide it by that 0.54 value. So we get a rate constant K will be equal to 129,629, and so on. We're already given our units here. We'll discuss units of rate constant here in a second, but that's molar to the -2 seconds to the -1. Now we have to take sig figs into account, so we have 2 sig figs, 2 sig figs, and 2 sig figs in all of our numbers. So this will come down to 1.3 times 10 to the 5th molar -2 seconds -2, which is what we would put into here. Now, if we were given the rate constant and those initial concentrations, we could utilize that to calculate the rate of the reaction as well. So knowing our rate law becomes a multivariable equation where we know all but one and can solve for that unknown variable. Now, how do we actually find these reaction orders? Since they're not determined by our balanced chemical equations, how do we find them? Yes, they can be just given to us for specific reactions, but for other reactions, depending on the amount of concentration, the temperature, those reaction orders are going to change. So the only way that we can find our rate constant K along with the reaction orders X and Y is we can only find them experimentally. Okay? And what we'll do is we will observe how the rate of a reaction will change as the concentrations of the reactants are changed. Because we know that the rate depends on the concentration over time. Okay, so if we change the concentration, the time at which the reaction occurs will then change. And we can see how those two values relate. This is called the method of initial rates. And the basic premise around that is a three-step process. First, we want to determine the value of X, which is our reaction order, okay, from the data in which reactant A varies and reactant B is constant. Then, once we have the reaction order with respect to X, we then want to determine the reaction order of Y. So we determine the value of Y from the data in which reactant B varies and reactant A is held constant. Now the reason we're looking at when one varies and one doesn't is because if we know that the concentration of only one reactant is varied and we see a big change in the rate, that big change would only be attributed to the reactant at which we change the concentration. We can't change both reactant concentrations at the same time because they may have different effects, different reaction orders that would affect the rate. So we'll find X and Y from our data and information about reactant A and B, and then once we know X and Y, we can determine the value of K, the rate constant, from one set of concentrations and the corresponding rate, just like we did in our previous problem where we were given concentrations and the rate, and then we solve for K. So let's look at an example of this together and work through this method of initial rates together. I'm going to hide my calculator just so I have a little bit more room. Okay. So again, we have the reaction A plus B goes to C plus D, and we have our generic rate law up here at the top. Rate is equal to K times the concentration of A raised to the X times the concentration of B raised to the Y. And what we want to do from this method of initial rates is find X, find Y, and find K. So we're given experimental data here in our chart where we ran 3 experiments. The first one counts as kind of like our baseline. Okay, that's going to be like our control group, okay? And then we ran 2 subsequent experiments. In the second experiment, the concentration of A varied, okay, it doubled, where in experiment 2, the concentration of B remained the same. Then in experiment 3, we brought back the concentration of A to the control. Okay, so we kept that constant in comparison to that control. But the concentration of B then changed. So we can see that as we change that, our rates also changed. So the rate of the reaction changed as we changed those concentrations. So we can utilize that information to find our reaction orders. And what we're going to find useful, an equation that we're going to find useful when we're doing this, is rate over rate is equal to concentration over concentration raised to the variable n, where that could be X or Y. And what this is doing is when we're looking at this specific reaction or this specific rate law here, in our first to second experiment, since we're only changing reactant A, the rate is only going to depend on this portion of our rate law. And if we're going to be comparing two experiments, well, we're just taking the rate and dividing the new rate, the concentration, dividing it by the new concentration, in order to find our last variable, n, or in this case for reactant A, x. Okay, so let's write this specifically for our reactant A. So we have rate of experiment 1 over rate of experiment 2, which will be equal to the concentration of A in experiment 1 and the concentration of A in experiment 2. And that will be raised to the x. Now again, since we're only looking for the reaction order with respect to x, okay, and reactant A, then we ignore reactant B because its concentration was held constant when we went between experiment 1 and experiment 2. So we know rate of 1, we know that rate from experiment 1, it's 2.1 times 10 to the minus 4. And the rate of experiment 2 is 4.2 times 10 to the minus 4. Okay. Our concentration of A in experiment 1 was 0.10, and our concentration of A in experiment 2 was 0.20. That is now raised to the x. So let's grab our calculator so we can simplify this. So now we have to simplify both sides so that we can solve for x. So we have 2.1 times 10 to the minus 4 divided by 4.2 times 10 to the minus 4. And that gets us a value of 0.5. And then we do 0.1 divided by 0.2. We get a value of 0.5 raised to the x. Now it just becomes exponent math, okay? What value of x what value does x have to be if I were to take 0.5 and raise it to some power in order to get 0.5? Well, you can do this on your calculator. 0.5, if I were to square it, gets me 0.25. That's not the correct answer. But I know 0.5 raised to the 1 gives me 0.5. So x has to be 1. Okay, do you see how we related that? What value does this x need to be to take that 0.5, raise it to some value to get out the required answer of 0.5? Well, it needs to be 1. Okay, so that means that x has a value of 1, and this is first order. In A. Okay, let's do now with B, which I'm going to jump to just a new slide so we have a little bit more room. So now we have B, and I've annotated my chart a little bit differently here. So A is now constant, B is now changing, as is the rate. So we can rewrite our little equation there as the rate of experiment 1 over the rate of experiment 3 is equal to the concentration of B in experiment 1 over the concentration of B in experiment 3, all raised to the y. So now, again, it just becomes like a plugging in of what we already know. So we know the rate of experiment 1 is 2.1 times 10 to the minus 4 over the rate of experiment 3, which is 8.4 times 10 to the minus 4. And that is going to be equal to the concentration of B in experiment 1, which is 0.015, divided by the concentration in experiment 3, 0.030, all raised to the y. So now let's simplify. We we have 2.1 times 10 to the minus 4 divided by 8.4 times 10 to the minus 4, and we get 0.25, and that's equal to 0.015 divided by 0.030, and that's a value of 0.5 raised to the y. So now we have to think, okay, if I take 0.5 and raise it to a value, okay, what value does y have to be to get out an answer of 0.25? Well, we know that 0.5 raised to the 1 gives us 0.5. If I take 0.5 and raise it to the 2, that now gives me my desired answer of 0.25. So y has to equal 2. So we're just looking for the value that the exponent has to be in order to have both sides of the equal sign be the same number. Okay, that's what an equal sign means. So y is then equal to 2. So this is then second order in B. So now we can rewrite our rate law and say that the rate is equal to K times the concentration of A raised to the 1 and the concentration of B raised to the 2. Now again, if it's a 1, we never really show that one, so we wouldn't have to show it. Okay, so that is our new rate law. So if we look back at our guidelines for the method of initial rates, we've done the first 2 bullet points. We determined the value of x and we determined the value of y. Now that we have those, we want to determine the value of k from one set of concentrations and the corresponding rate. So we have 3 different experiments to choose from where we know the concentration of A and B, and we know the rate for 3 different experiments. As long as you're pulling the information from the same experiment, you can find the rate constant because the rate constant will be the same for all 3 experiments. So you can choose any 3 experiments that you want. You can choose the first one, the second one, the third one. I'm going to choose the first one. If you want to do this calculation with me but use the second one or the third one and double check or make it believe in your own head that you can use any of these experiments to get the same value, feel free to do that. I'm going to use the information from experiment 1. So we know our rate from experiment 1 is 2.1 times 10 to the minus 4. That's equal to K, which we're searching for, times the concentration of A from experiment 1 is 0.10, and the concentration of B from experiment 1 is 0.015. And we're going to raise that to the 2 because we found our reaction order with respect to B was second order. So now this just becomes algebra. 0.1 times 0.015 squared. So we get 2.1 times 10 to the minus 4 is equal to 2.25 times 10 to the minus 5 times K. So we'll take that rate, that 2.1 times 10 to the minus 4. We'll divide that by 2.25 times 10 to the minus 5. And we get a K that is equal to 9.3. We have 2 sig figs throughout this, so we'll keep it at 2. So let's keep practicing with our method of initial rates. So here we have some initial measurements of the initial rate at a certain reaction, okay, and it's given by this table. We want to determine first the rate law, okay, so we need to find the reaction orders. for both N2 and H2 so that we can write the rate law, and then we need to use that rate law to calculate K. So what I want you to do is pause your own video, and using what we did in our previous problems, attempt solving this problem using our method of initial rate. So finding the reaction order with respect to one reactant and then the other reactant, and then using those reaction orders to find the K. So if we want to find the reaction order with respect to N2 to nitrogen, we have to look at the two experiments where only the concentration of nitrogen varies. So that would be the first and the second. Noting that in the first and the second, the concentration of my other reactant that I'm not looking for at this time remains constant. So for nitrogen, we're going to take the rate of the first one and we're going to divide that by the rate of the second and set that equal to the ratio of the concentrations. So 0.155 and 0.493 raised to the x. So we'll simplify 3.0 times 10 to the 3, 3.03 times 10 to the 4. Keep a few decimal places just to make sure. It helps make the finding of the reaction order a little bit easier, to make sure you're getting as close to a whole number as possible. And then we'll do 0.155 divided by 0.493. We get 0.3144 raised to the x. So now with a lot of these problems, it's not as simple to find that x value as it was in our previous example, where it was really nice to see 0.5s, eat like solid numbers. We're not always going to have that. So we need to think of how we can take 0.3144 and square it, cube it. It's obviously not raised to the 1, so let's start with squaring it. Now this is why I said keep a lot of decimal places. It's not going to be perfect. Okay, we're not looking for a perfect match. Okay, again, we don't have perfect whole numbers. So if we took 0.31440162227 and squared that, we'd probably get something a little bit closer. Now we're getting a few more decimal places. We're pretty close to where we were. Now it's, again, not going to be spot on. So here, our x would be 2. Again, it's not perfect, but we can't have like 2.1 or anything like that, so don't try to do point. Right, it's not going to be a decimal. It's not don't try to spend your time getting these perfectly the same, because it doesn't really matter, because our reaction orders are really going to just be integers, and only rarely would they be fractions, and that fraction is most likely 0.5 or 1/2. So our reaction order here is 2. Now we can move on to hydrogen. If we look, hydrogen changes between 2 and 3, but also between 2 and 3, nitrogen changes. So we can't use a ratio of 2 and 3 because the rate is being affected by nitrogen. So again, it's always better to compare to your control. That first experiment is always going to be your control. So let's erase these. Hydrogen is changing between 1 and 3, whereas in 1 and 3, nitrogen is constant. So we want to use 1 and 3 for hydrogen, not 2 and 3. even though the concentrations are different. You have to look at the concentration of the other reactant as well and make sure that that is unchanging. So we can set up our equation again. We can do the rate of 1, 3.0 times 10 to the 3, over the rate of 3, 87.7, which is equal to the concentration of hydrogen in 1, so 2.1, over the concentration in 3.359. And that will be raised to the y. So now we simplify 3.0 times 10 to the 3 divided by 87.7. We get 34.2075 is equal to 2.1 divided by 0.359. And we get 5.849. 58 on there, raised to the y. So now we have to find our exponent of y. We know that it's not 1 because they're not the same value, okay? So now let's try squaring it. Perfect. Squaring it gives us y of 2. If we take that 5.8 and square it, we get 34.2. So y is 2. Therefore, our rate, if we were to fill in our answer like in our ALEKS homework, our rate is then equal to K times the concentration of N2 squared times the concentration of H2 squared. So that's the first part of our problem. So we found our reaction order with respect to N2 and H2. Now we have to calculate K. So in order to do that, we have to choose one of our experiments. Let's go crazy and let's choose experiment 2 this time. You could choose experiment 1, you could choose experiment 3. It doesn't matter, whichever one you choose, as long as all the numbers are coming from the same experiment, you will still get the correct value of K. So we get rate, we know the rate. Our rate for the second one is 3.03 times 10 to the 4 is equal to K times the concentration of nitrogen, 0.493, and we're going to square that, times the concentration of H2, 2.10, and we're going to square that as well. So now we simplify. 0.493 squared times 2.1 squared, and then we'll take 3.03 times 10 to the 4 and divide it by that value. And we get a K that is equal to 28,268. And let's see, we have 3 sig figs in here. So this would be 2.83 times 10, 1, 2, 3, 4 to the 4th. And for right now, for what I'm showing right now, we're not going to worry about our units of K. We'll learn about those units here in a few slides. So once we learn about those, and when you go to put your answer in for your ALEKS homework, you will have to have units on this value of K. So 2.83 times 10 to the 4. Units are to be determined. Okay. So let's take another approach to this, similar to what we've done in the past. So a certain reaction is first order in hydrogen and first order in iodine. Use this information to complete the table below. Be sure each of your answer entries has the correct number of significant digits. So we know that we know our reaction orders. So if we know our reaction orders, then we know our rate law. So we can automatically write our rate law. Rate is equal to K times the concentration of hydrogen, it's first order, and multiplied by the concentration of iodine, also first order. So there is our rate law that we can use for this problem. We now want to find the rate of each reaction. That's what the problem is looking for. We're given information about one set of data where we know the rate and we know the concentrations. So what we can do first is use experiment 1 to calculate K, and then use K to calculate rate in experiment 2 and 3. So we know our rate law, we know what we have to do, so pause your video and start solving these two portions of this problem. So our first step is to use experiment 1 to calculate K, which we've done multiple times now. So we know the rate is equal to K times the concentration of H2 times the concentration of I2. And now we can just simplify. So 0.113 times 1.33, then we're going to take that 5.0, 10 to the 4th, and divide it by that number. So we get a K of 3.33 times 10 to the, let's see, 5 for our K. Okay, so we know K now, and we can use that to calculate the rates in experiment 2 and 3. So rate in experiment 2 is equal to K, 3.33 times 10 to the 5th, times our concentration of H2, 0.113, times our concentration of I2, 0.446. So we'll take that 3.33, multiply that by 0.113, and multiply that by 0.446. And we get a rate of 1.68 times 10 to the 4 molar per second. So that would be our rate for reaction 2. And then our rate for reaction 3 is set up in the same way. We'll use that K since it's a constant, and we'll multiply it by our new concentrations, 0.0273 and 5.51. So we'll take 3.33 times 10 to the 5th, multiply that by 0.0273, and multiply that by 5.51. And we get a rate of 5.01 times 10 to the 4 molar per second. Okay, so let's talk about our units of a rate constant, which I said previously was to be determined. Okay, so the units of the rate constant will depend on the overall order of the reaction. So it will change. They are not constant. Even though the number is constant for a given reaction, the units for K are not all the same. So if the overall reaction order is 0, the units of K will be molar per second. I know sometimes seeing things to the -1 are difficult to see, so I'll try to write these in fraction form as well. So that would be molar per second. And that's because the rate is equal to K in a reaction that has an overall order of 0. And our units of rate are molar per second. If the reaction order is 1, then the units of K are 1 over seconds. And this is because, if I can show my math down here, if I know that rate is molar per second, okay, K, if I'm looking for my units of K, multiplied by my concentration of one of my reactants, well, we know concentration is molar. So in order to get my K times concentration side equal to my rate units, I need to put my K as 1 over seconds. That way when I do 1 over seconds times molarity, that equals molarity per second, which is equal to rate. So my K for a first order reaction has a unit of 1 over seconds. If the overall reaction order is 2, then the units of K are 1 over molar times seconds. And again, this is for a similar reason. So again, I need my rate to be equal to molar per second. That's the unit of rate. So now I'm looking at my unit of K in relation to either my concentration being squared or having two concentrations. It would end up being molar squared, right? If I have molar times molar, that would be molar squared. If I have molar and then I square it, it would end up being squared. So my units of K have to be 1 over molar times seconds, so that this molar cancels out with one of these molars, and I'm left with units of molar per second. And finally, if the overall reaction order is 3, then the units of K will be 1 over molar squared times seconds. Again, for a similar reason, if I have a reaction order of 3, my molar contribution is cubed, so I need to balance that out with a molar squared times seconds. Now you'll notice that in each K we always have a seconds over 1, because that's the only way that we're going to get that second notation that relates to our rate. Okay, the only thing that changes is the molarity. And the way that I like to think about it is that the exponent on the molarity, if you were to just look at the number, so in this case 1, if you add 1 to it, then you get the reaction order. So molar is raised to the 1, add 1 to that, it's 2, the reaction order is 2. Molar here is 2, add 1 to that, it's 3, the reaction order is 3. Since there is no molar here, it'd be molar to the 0, 0 plus 1 is 1, reaction order of 1. Okay, so there's multiple ways to remember this. You can first think about how the math works out and show your units, or you can think of adding 1 to the exponent of the molarity. You can think of it that way. So if you were to go back and do the problems that we've discussed previously, your answers, specifically in your ALEKS homework, need to have units of K attached to them that is corresponding to the overall reaction order, because those units will vary depending on the reaction order. So let's practice another method of initial rates problem, where now when we solve for K, we can use our units appropriately. So again, we're going to, for method of initial rates, we're going to first find our reaction orders with respect to N2 and H2, and then we'll use that rate law to calculate K. Okay. So pause your video and attempt this method of initial rates problem. Okay, keep practicing these. You're going to see a lot of them on your homework and exams. So practice this problem. Try to get all the way through to calculating K, and then use your chart from your notepad to try and determine the units of K. Okay, let's start with finding nitrogen, N2. Let's look at where its concentrations vary. So it starts off in its control as 0.33 molar, and in experiment 3, that's when its concentration varies. And we can see that in 1 and 3, the concentration of hydrogen is constant, so we can use those two experiments. So we'll take the rate of 1, we'll divide it by the rate of 3, and set that equal to the concentration in 1 over the concentration in 3. We're going to raise that to the x. So we get 5.0 times 10 to the 5th divided by 8.74 times 10 to the 6th. We get 0.057208 is equal to 1.33 divided by 5.56. We get 0.2392 raised to the x. So we know x isn't 1, so let's try squaring it. Squaring it gets us pretty close, so x is going to be equal to 2. And now we can move on to hydrogen. So again, let's look at where hydrogen's concentration changes. Well, it changes from 1 and 2, and the concentration of nitrogen stays constant, so we can use 1 and 2 to compare for hydrogen. So our rate of 1 is 5.0 times 10 to the 5th, and our rate of 2 is 2.20 times 10 to the 5th. That's equal to the concentration of hydrogen in 1 over the concentration of hydrogen in 2 raised to the y. Now we simplify 5.0 times 10 to the 5th divided by 2.20 times 10 to the 5th. So we get 2.27. And then we take 1.64 divided by 0.723. We get 2.268, which are basically the same number, so y is going to be 1. Again, these are going to be integer values. Don't try to match them up perfectly down to the very last decimal. It's not going to work. As long as you're within a 1/10th or a 100th of a decimal place, then you're fine. Okay? It'll be very obvious if it's not correct. So we're looking for 1s, 2s, 3s, and so on. Don't try to go crazy with any decimals. Okay, so that now tells us our rate law. So rate is equal to K, concentration of N2 squared, concentration of H2 to the 1. And now we can use any of our data to find the K value. So I'm going to use 3. I've already done 1, I've already done 2, so let's do 3 now. So let's take the information from experiment 3. We know the rate, 8.74 times 10 to the 6 is equal to K times the concentration, 5.56, which we will square, and the concentration of hydrogen, 1.64. Okay, so we'll take 5.56, we'll square it, and multiply that by 1.64. And then we'll take that 8.74 times 10 to the 6 and divide it by that number. And we get a value of K. Let's see, we have 3 sig figs, so let's give it a 1.72 times 10 to the 5th. So now we have to look at our units. Well, overall, the reaction order overall is equal to 3, so it's third order. So you can again think of it this way. We have molar cubed. I need to put something here to make it equal molar per second. Well, I need to cancel out 2 of those molars, and my per second comes from my K anyways. So our answer would be 1 over molar squared times seconds. Or you can think of it as, okay, this is 3, which means my molar needs to be, if I do it in the fraction, it's going to be 2 times seconds because K always has units of 1 over seconds. You could do it either way. So K is 1.72 times 10 to the 5th, 1 over molar squared times seconds.